So what is a one-sample t-test? A one-sample t-test is used to determine whether the mean of a single continuous variable differs from a specified constant. Essentially, what you're trying to do here is you've got one column of data, it's continuous data, and you're trying to say, is this data, this column of data, different than a variable that I have told you what it is? So, for example, if we're looking at something like IQ, intelligence quotient, a number that's thrown around for that is that the mean IQ is around 100. If you have a sample from some undergrads that you were surveying, for example, you ask them their IQ or you test their IQ, you get a column of data for what their IQ might be. You might compare it to this number of 100 to say, is this the same? Is this different? A one-sample t-test is a parametric test. It assumes normality. The data from your column of data should follow this approximate bell-shaped curve, highest in the middle, lowest at the ends. And I left you some links in the slide. We've got the SPSS LibGuide. Layered statistics is one we haven't written, but I think it's a really good resource. Or you can go to the SPSS documentation for additional help on running a one-sample t-test. What are our assumptions of a one-sample t-test? There are 4 of them we're going to talk about. The first is that you have one continuous variable. You only need one variable, and it must be continuous. We'll cover that on our next slide. Our second is a bit of a tricky concept for some folks. Our second one is data must be independent. This is generally not something you check after the fact. This is generally something you do before you run your survey or your experiment. So, for example, if I was doing, let's pick on intelligence again. I've got a class of students. I want to check their intelligence and compare against some number that I've already specified. I will only have one row for each participant in my data set. The data must be independent, i.e. I can't have, say, Susan within my class. I can't have Susan's data 5 times in my spreadsheet. That's cheating. The data must be independent, one row per participant, no links between the participants. Points 3 and 4, we can check them together in our software. Number 3 is the variable is approximately normally distributed. So we've already talked about this. It has to follow that approximate bell-shaped curve. And number 4 is that there should be no significant outliers in our data set in that specific variable. So we will cover those on the next few slides. Let us continue. So our one-sample t-test, checking the assumption of continuity. You must have continuous data. If we are using fake data 1 from our fake data set today, we can look at this variable and say, does this look approximately continuous? Does it look like we've either got decimal points, a range of values? We don't just have 3 buckets, for example. We've got a bunch of different values. And here we pass the assumption of, we pass the continuous assumption because the data in fake data 1, we've got a bunch of decimals. We've covered this before. It looks continuous. One sample t-test, checking the assumption of independence. We've covered this. Actually, we haven't covered this one at all. This is our first test where we're actually checking independence. And like I've mentioned, we generally have this set up before we get to this stage, the data analysis stage. Generally, you have this set up before you've even run your survey or your experiment. You've made it so that you've only got 1 row per participant. No cheating. You don't want someone to have multiple rows. So if we were to look now and be like, does this look continuous? Well, we've got, for example, in row 1, we've got someone who identifies as male. They've got a fake data 1 score, fake data 2 score, fake data 3. We've got some information for them, and it looks different than the other rows. So we can't be certain at this later stage whether the data are independent, but it looks like they are because it looks like each of these folks is a separate person. So again, you normally want to check this one before you get to this stage. And then our one sample t-test, checking the assumption of normality and outliers. We do this at the same time within the SPSS software, depending how you're checking your outliers. You want to click on Analyze, Descriptive Statistics, and Explore. So for normality, again, we're checking to see, does the data in that fake data 1 column approximate a normal bell-shaped curve? Does it look like the bulk of the data is highest in the middle with just a little bit at the ends? This test assumes the data are normal, and if the data are not normal, you might not be able to use this test. And with outliers, we want to be careful because if you have any, for example, extreme outliers, someone who's really far away from the rest of your data, they're going to potentially be skewing your data, so the results of your test might not be reliable. So you want to be checking for normality and outliers anytime you're doing a one-sample t-test. So again, if you're doing this on our little fake data set or on your own data, you're going to click Analyze, Descriptive Statistics, Explore. That will open up the Explore dialog box. This is where you can check both normality and outliers. What you're going to do is you're going to take your one continuous variable. Here we're going to use fake data 1. And you take it from the left side, you click the blue arrow, and you put it where it says Dependent List. Continuous data points should have a little yellow ruler next to them. That indicates you've set your measure properly. If you instead have 3 circles or a little bar graph, you don't have a yellow ruler, you're not doing the appropriate test, or your data is not set up properly and you have to go and fix that. So if we've moved our fake data set or a fake data column to the dependent list box, we can click where it says plots. And there's a few things you want to check here to make sure your output's going to be correct for you. So under descriptive, we want to uncheck stem and leaf. We don't normally use those. You want to check where it says histogram. You do want to see a histogram. You also want to click where it says normality plots with tests. This will give you a statistic to look at. And you want to click continue. Once you've done all that, you've moved the one thing that you're looking at, you've checked which options you want in your output, you've said continue, you can click OK. And what this will give you is it will give you both normality and outliers in the same output. So it'll look something like this. Again, we're looking first for that normal bell-shaped curve for normality. It'll give you a table that says tests of normality. It's not quite at the top. You have to scroll down just a little bit. But it'll give you a table that says test of normality. We're checking to see with a statistic whether we follow that bell-shaped pattern. Here, if we have a p-value less than 0.05, it means that this value is statistically significant and we have failed normality. There is a problem. You need to stop. You cannot do this test. If you have a p-value greater than 0.05, it means you have passed normality and you're doing okay. You're allowed to keep going with this test. It gives you 2 different p-values in this output. On the right-hand side, we have the Shapiro-Wilk statistic where it says Shapiro-Wilk sig. Our value is 0.455, which means we've passed normality. It also gives you a little bit to the left the Kolmogorov-Smirnov statistic where it says KS sig. That's 0.200. With that, we have also passed normality. Generally, if you have 50 or fewer observations, you want to be looking where it says Shapiro-Wilk, so that's the one we'll be using today. So statistically, we have passed normality for this fake data set. Some researchers also like to do what's called visual inspection. So they'll create some graphs and look at the graphs to determine, does it look approximately normal? If you were in the workshop last week, you've already seen this data set, but we'll cover it again in case anyone's new. You have asked if you've checked histogram to generate a histogram for visual inspection. What we're looking at here is to see whether this histogram looks similar to our typical bell-shaped curve with data highest in the middle and lowest at the ends. It's not perfect. Our ends are sometimes a little high, sometimes a little low, just depending where it is. But we can see that this roughly matches our bell-shaped curve, so we've passed visual inspection using histogram. We can also look at what's called a QQ plot. That should also be in your output. This has a bar going up to the right. And what you're looking for here is that your data points, yours will be blue, mine are red because I've changed them for the presentation. But your data points should fall pretty close to or on that line. If your data points follow that line pretty closely, it means you've passed visual inspection for the QQ plot. If your data points are all over the place, nowhere near the line, you've probably failed. So in our fake data set, we have a statistic and 2 graphs that all say we've passed normality. We are allowed to use the one sample t-test for this data. That's normality. We can also look at outliers in the same output file. SPSS does outliers using the box plot method, so it will have generated a box plot for you. There are other ways to look at outliers. So for example, a lot of folks will do something like look at the mean of this group, look at the standard deviation. If you're a certain distance away from the mean, we'll call you an outlier. SPSS doesn't make that super easy to calculate, but it makes box plots really easy. So if you're cool with box plots, we can use the box plot method. The dark bar in the middle here is our median. We also have our interquartile range. And we have what we call our whiskers. So up here and down here, those are the whiskers showing essentially where the bulk of the data is going to be. Using the box plot method, what you're looking for is any data points that fall outside of the whiskers, either really far above or really far below the data. We don't actually have any outliers in this specific variable. But if you had your own data, if you have a circle with a number next to it, that's telling you which row of your data set is an outlier. So if it said 22, that's row 22 of your data set. If it had a star with a number next to it, that's even more problematic. So let's say it was a star with a 25. That's telling you that row 25 of your data set is an extreme outlier. They're really far away from the rest of the data. So we want to be careful with outliers, because if we have outliers, they might skew our analysis or skew our data so far away that it looks like one thing when maybe it's something else. So we've passed normality and we've passed outliers. Okay, how do you actually conduct a one sample t-test? If you have passed all of your assumptions and you're looking to run this for the first time, you can click where it says Analyze, Compare Means and Proportions, One Sample T-Test. You might have noticed if you've come to a few workshops by now, SPSS hides stuff all in these weird terms. This one at least has the name of the test listed. So Analyze, Compare Means and Proportions, One Sample T-Test. If you've passed your assumptions, you're ready to run the test. Analyze, Compare Means and Proportions, One Sample T-Test. That will open the One Sample T-Test dialog box. What you do here is you take your one variable, which should have a little yellow ruler next to it, and you put it where it says Test Variables. So here we move fake data 1 to where it says Test Variables. Just below that, it says Test Value. You have to say which number you are comparing against. This might be a number from the literature. So if you're in a research area that's looking at, I don't know, weight of cats, maybe the average weight of cats from your literature search is 12 pounds. Maybe they're big cats. You could put in 12 here if that's the kind of data you're looking for. Maybe it's just something you're looking at against, I don't know, Statistics Canada says the mean of something is blank. You might take that mean, you might put it in here and say, is the mean of my sample different from Statistics Canada's means? So this is the part where you need to know what number you're comparing against. So you type in your number. Today we're using 85. It's a fake data set. We're looking to see, is this column of data different than the value of 85 for whatever reason? This could be a happiness score. This could be an average on a test. Could be a lot of things, but it's fake data, so we're just going to pick 85. And we make sure the box that says Estimate Effect Sizes is checked. And then we click OK. So all you need, move the one variable over, put in your test value, click OK. If you do that, you will get some output that looks like this. There's a bunch of different information that comes out. So for example, the first thing it gives you is a one sample statistic table. It tells you your N, or number of observations. It gives you some information like your mean and your standard deviation. Where you're going to look for the result of your test is the next table where it says one sample test. It gives you a t value, which is important if you're writing this in a scholarly publication, for example. It gives you your degrees of freedom, also important if you're writing this in a paper. It gives you significance here. You could use a one-sided p-value, fancy way of saying, hey, one-sided, you're only looking to see if it's different in one direction. Two-sided is you don't care which way it might be different. You're going to look on both sides. The standard for a lot of fields is to look at the two-sided value unless you had a reason to use a one-sided value. So we're going to look where it says two-sided p. Here, p is less than 0.05. If your p-value is less than 0.05, you have found statistical significance. This means that your value, your mean value for that variable, is different, either higher or lower, than that test value that you've indicated. So here, our mean is actually 87. We can see our mean up here. And we're checking to see whether the mean of our column is statistically significantly different than the value of 85. Our p-value says, yes, it is different. And because our mean is higher than the test value, we can say that our mean is greater. Our variable, maybe our people are happier, maybe our people are smarter. Our value is higher than the test value. We also get a one sample effect sizes table down here. The effect size for this test, i.e. how big is this difference? How big is this t-test that we're doing? How large is it? Is Cohen's d. That's our effect size. So it gives you, you'll generally be looking at, I think where it says point estimate, you might be looking at standardizer, or you might be looking at point estimate, and it also gives you a confidence interval to tell you 95% confidence in that specific measure. So the biggest thing you need to look at here is your p-value. Is this different? If p is less than 0.05, you found statistical significance. There is a difference. Yours is either higher or lower than that test value you've indicated. If p is greater than 0.05, we fail to be able to say whether there's a difference.